Today we are going to start on electrochemistry part 1, which is essentially the galvanic cell.
So what exactly is electrochemistry? It is actually the study of the interconversion of electrical and chemical energy, and we harness the electrical energy in the movement of electrons from one chemical species to another. The basis for electrochemistry is actually redox reaction, and there are two types of electrochemical cells that we are learning in this topic, which is galvanic cells as well as electrolytic cells, which I think has been covered in your Sec 3 and Sec 4 syllabus. The topic of electrochemistry has been gaining importance over the past few years. What we have been familiar are the use of batteries to power our daily electrical appliance. Over the years, due to the concern over climate change, global warming, there is a need to reduce our reliance on fossil fuels. That's why the push to adopt EV, which means electric vehicles. Okay, and for local news, our own company, ComfortDelGro, is expanding the use of fuel cell bus. Okay, now in traditional vehicles which are powered by internal combustion engine, fossil fuel or petrol is combusted, and the energy released by the burning of the fuel will power the pistons in the engine in traditional vehicles. But in electric vehicles, we are using the movement of electrons, which is essentially the electric current, to power the motor, and this motor will then drive the electric vehicle forward. Okay, so there are a few competing technologies in electric vehicles. Okay, so some are powered by batteries, some are powered using hydrogen as a potential fuel. Okay, but the burning of hydrogen gas will produce electrons, which is then harnessed as a current. The advantage of using hydrogen gas is, of course, the product of the combustion of hydrogen gas will produce water, which is not a pollutant. Okay, so we will take a look at this picture again in later lectures. So for lecture 1 in electrochemistry, we need to learn what is galvanic cell, the term electrode potential, as well as the term standard electrode potential. Okay, so for a galvanic cell, in a galvanic cell, the redox reaction is spontaneous. The chemical energy is converted into electrical energy, and this can be harnessed in the form of electric current. Okay. For electrolytic cell, the opposite is that the redox reaction is non-spontaneous. You need electrical energy to be converted to chemical energy. Instead, current is used to drive a non-spontaneous chemical reaction. Now we'll take a look at a redox process that can be carried out in the lab. We will now put a clean zinc strip into a solution that contains the ionic salt called copper nitrate. So after maybe a few hours, you will notice that the zinc strip has something that is deposited for the part that comes into contact with the blue copper 2 plus solution. And you also notice that after some time, the color intensity of the blue solution has decreased, which essentially means it becomes less blue in color. So this one has become less blue. So can we try to explain why? So the solid that is actually deposited on the zinc strip is actually copper. You also notice that the blue color has started to fade away. And in fact, if your eyes are sharp, you will notice that the zinc strip has started to corrode or erode. What exactly has happened to the zinc strip in the blue solution? So a chemical reaction has taken place. It is a spontaneous reaction. Okay, we know that the zinc solid and the copper 2 plus solution are in contact. So basically what is happening is a redox reaction has happened. The zinc strip has been oxidized to zinc 2 plus aqueous, while the copper 2 plus aqueous has been reduced to copper solid. Okay, so the limitation of this experiment is we cannot harness the energy that has been released. Okay, so is there a way that we can modify this setup to harness the electrical current that can be produced? That is where this topic is going to. We need to set up a galvanic cell. And before we end this particular slide, some of you may know this reaction as the displacement reaction because we have learned this in Sec 3 or Sec 4. Zinc is a more reactive metal than copper, therefore it can displace its copper 2 plus ions from the solution. What we will do now is to take a look at a video about the galvanic cell that involves copper and zinc.
When a strip of zinc metal is immersed in an aqueous copper 2 sulfate solution, electrons are transferred from zinc to the copper 2 ions. Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc 2 ions, which enter the solution. This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown. The spontaneous copper-zinc oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper 2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper 2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through the external circuit from anode to cathode.
So for the galvanic cell that we are examining now that involves zinc and copper, you notice what is different now is we have separated the zinc from the copper. So this separation is known as producing or setting up two half cells, and then these two half cells are connected by wires as well as a salt bridge. So we have the zinc half cell that involves the zinc 2 plus aqueous and zinc solid half cell, as well as the copper half cell that involves the copper 2 plus aqueous and copper solid half cell. Okay, so there will be an anode and a cathode, and there will also be a salt bridge that contains a salt solution, Na plus, NO3 minus, or K plus and SO42 minus ions. So we will now take a look at this half cell in greater detail. So what we notice is that when we have connected everything is in a complete circuit, the light bulb glows, which means there must be electrical current flowing through the circuit. We also notice that for the copper half cell, the color of the solution become less blue, okay, and then for the copper electrode, it will increase in size, while that of the zinc electrode, it will decrease in size. So can we explain in terms of chemical process what has exactly happened to this uh, galvanic cell? Okay, so on the zinc side, the zinc solid is oxidized to form zinc 2 plus aqueous. And in the process, there will be electrons that will be released, and these electrons will stay on the zinc electrode. Okay, so at that side, the zinc is the anode as oxidation occurs, and because the electron stays on the zinc electrode at that particular moment, it is a negatively charged electrode, or you can call it the negative electrode. While on the copper side, the copper 2 plus ions will first, the copper 2 plus ions in the solution or in the water will first gain electrons from the copper solid, which is the copper electrode, and there will be more copper that is deposited on the copper electrode. The copper is the cathode. This is because reduction occurs there, and because the copper 2 plus first takes away the electrons from the copper solid, which is the copper electrode, at that moment, the copper electrode is positively charged. So it is a positive electrode. The use of the salt bridge and the wires in red that you see on the diagram helps to ensure a complete circuit so that the electrical current can flow. So what is found in the salt bridge are salt solution like sodium nitrate or potassium sulfate. Okay, so the purpose of a salt bridge is to prevent the solutions in the two half cells to come into contact with each other. It also allows ions like sodium plus and nitrate anion to flow into the two half cells. Okay, so you can regard a salt bridge as a liquid wire. Now let's take a look at what is happening to the salt bridge in greater detail. So for the zinc half cell, you know that the zinc solid is being oxidized to zinc 2 plus. What will mean is that the zinc 2 plus concentration in water will increase. And when the zinc 2 plus concentration in water increase, that means there will be more Zn2 plus than N ions in the half cell now. So the total positive charge will overwhelm the total negative charge in the zinc half cell. So the solution becomes positively charged. Okay, for the copper half cell, there will be more copper 2 plus, there will be less copper 2 plus in water because the copper 2 plus has reduced to form copper. So now there will be more NO3 minus than copper 2 plus in terms of total charge. So the solution will become negatively charged. So then you ask me why this is not ideal when the solution becomes charged. If you take a look at the diagram at the top right, you need electrons to flow from left to right in this particular galvanic cell. So if the solution becomes charged, right, then the electrons will not flow through the external wire, because on the left hand side, the electrons will be attracted back into the zinc half cell because the solution is positively charged. On the right hand side for the copper half cell, the electrons will not go into the copper electrode because like charges repel, because the solution on the right hand side is negatively charged. So this is not good. Okay, so how can we prevent this? This is where the salt bridge comes into play. So to prevent the solution on the left side becoming positively charged, NO3 minus will go into the zinc half cell. Okay, and then sodium plus in the salt bridge will goes into the copper half cell. So that will allow the electrical current to flow from left to right in the external wires. So there you have it. This is how you should draw a galvanic cell that involves zinc and copper. In this particular galvanic cell, the electrons flow from left to right in the external wires, and in order to ensure a complete circuit, a salt bridge is also need to be included in this setup. Okay, so what you need to know for drawing a galvanic cell and understanding a galvanic cell is anode is the place where oxidation occurs, while cathode is the place where reduction occurs. The electromotive force of a galvanic cell can be measured using an instrument called the voltmeter. Okay, so the electromotive force is also known as the potential difference between the two electrodes. Okay, so for chemistry or for this topic, we call it the cell potential. But however, if you use the word standard cell potential, it is actually when two half cells are carried out under standard conditions. As in, what is standard conditions? I think you have learned it in your JC1 topic called chemical energetics. We will look at the standard conditions later in another slide. Okay, so to jump the gun, the electrode potential of a cell is actually related to the change in Gibbs free energy. Now, what exactly is electrode potential for a particular half cell? Let's imagine when you put a metal strip into a solution that contains its own ions. Okay, so a so-called the metal will lose electrons to exist as the metal aqueous ions in water. Okay, for example. So what we will have is that the metal strip will become positively charged, while there will be negative charge that is built on the surface of the metal strip. Okay, so this is a dynamic process, which means a dynamic equilibrium will be set up whereby there will be the metal solid losing electrons and the metal cations gaining electrons. That means one is from left to right and one is from right to left in a reversible equation. So as a result, there will be an electrode potential that will be set up. So if you take a look at this picture, you will realize that there is a positive charge that will exist on the, there will be a negative charge that exists on the metal and a positive charge due to the metal cations surrounding the metal solids. So this means there is a separation of charge between the metal solid and its metal ions in water. So this will give rise to a potential difference, and we call this electrode potential or absolute electrode potential for this particular half cell. Now, as mentioned at the start of this lecture, we need to know what is the meaning of this term called electrode potential. So before we touch on this term, we have to ensure that we follow the convention. So we will write it in this particular manner where the metal cation is reduced to form the metal solid. This is the default direction for electrochemistry, where we write the reversible reaction in terms of reduction. Okay. So when you see an expression that says capital E Mn plus Aq slash M solids, you always read from left to right. We call this the reduction potential, which is also known as the electrode potential. So as has been mentioned in the previous slides, we always write the reversible equation in terms of reduction from left to right. Okay, so the value of the electrode potential will depend on the position of equilibrium. So if you have a very positive electrode potential value, it means that the position of equilibrium lies to the right. Reduction is favored. If you see a negative electrode potential, it means that the position of equilibrium lies to the left. Oxidation is favored. Okay, if your eyes are sharp, you realize that for non-metals, Non-metals like to be reduced. That's why they have a positive electrode potential. And for metals, they like to be oxidized. That's why they have a negative electrode potential. We will now look at the factors that will affect the value of electrode potential. There are 4 factors. They are nature of the metal or the identity of the metal, concentration of the Mn plus ions in water, temperature, as well as pressure. Now, for a highly electropositive metal, because the identity of metal makes a difference to the value of the electrode potential, for metals, they tend to lose electrons, which means their position of equilibrium lies to the left. So for a very reactive metal, that means they tend to lose electrons, their electrode potential values becomes more negative. Okay, so if you look at the table here, sodium is a more reactive metal than zinc. That's why the electrode potential is more negative, because sodium loses its electrons more easily as compared to zinc. Now for the second factor, which is the concentration of the Mn plus ions in water, if the concentration of Mn plus in water drops, that means the position of equilibrium will shift to the left, which means oxidation is favored. The electrode potential value becomes more negative. Okay, so this is actually Le Chatelier's principle at work. The third factor is temperature. In general, when temperature increase, solubility of substances increase. So for this particular case, when I increase the temperature, more metal solid will dissolve to form the metal aqueous cations. Okay, so it means that the position of equilibrium has shifted to the left. Oxidation is favored, so the electrode potential value becomes more negative. For the last factor that affects electrode potential value, as you have guessed, pressure only affects species that are in gaseous states. So we can give the reduction of chlorine gas to give chloride anions as an example. So when pressure increase, the POE or the position of equilibrium will shift to the right. Therefore, reduction is favored. The electrode potential value should become more positive at a higher pressure. We have come to the term called standard electrode potential. And before I start explaining in detail, remember the setup for zinc and copper. Electrical current can only flow if there are two half cells that are connected in terms of external wires and a short bridge. So to measure the standard electrode potential of a half cell, it needs to be connected or combined with another half cell. Okay, so we need to choose something called a reference electrode. And this reference electrode is called SHE in short, not the SHE pop group, but it stands for standard hydrogen electrode. So we are learning more about the term called standard electrode potential, and the way to write or represent standard electrode potential is capital E with a superscript that I have just circled in red. So if you see this particular superscript together with the capital E, it stands for standard electrode potential. As you have learned, there are 4 factors that will affect standard electrode potential: the concentration, temperature, and pressure. So it is important to standardize what are the conditions, okay, for standard electrode potential. So to measure standard electrode potential, the temperature is 298 Kelvin, the pressure is 1 bar. The concentration for aqueous ions is 1 mole per dm cube. Okay, and then if there is a electrode to be used and it should not affect the half cell, then we need to use an inert electrode called the platinum electrode. I will come to this in later slides, so don't worry. And the voltmeter that we use to measure the potential difference has to have high resistance. Okay. As mentioned in one of the previous slide, it is impossible to measure the electrode potential of one half cell. This half cell needs to be connected to another half cell so that the potential difference can be measured between these two half cells in a complete circuit. Okay, so this chosen half cell is also known as the reference electrode. It has a assigned standard electrode potential value of 0. Okay, this reference electrode is known as SHE, which stands for standard hydrogen electrode. So any half cell that is connected to the SHE will have a standard electrode potential value. So we need to know how to define a standard electrode potential. So please take some time to read through the definitions. We also need to know what is a standard hydrogen electrode. You will also need to know how to draw the standard hydrogen electrode. As mentioned in the previous slide, we need to know how to draw the standard hydrogen electrode, and the potential value associated with this standard hydrogen electrode is 0 because it is the reference half cell. So the hydrogen gas can be introduced into the solution using this setup as shown. So the hydrogen gas has to be at 298 Kelvin and 1 bar. The aqueous ions of H plus has to be at 1 mole per dm cube and 298 Kelvin. And the electrode used is an inert electrode, which is platinum. So we need to know how to draw all this and label all the parts accordingly. Okay, so please take note. If you use other conditions not at 298 Kelvin or not at 1 bar, then the electrode potential of this hydrogen half cell is not 0. As you have noticed from the previous slides, you will notice that there are different types of half cells. Actually, there are 3. So the first one is a metal in contact with its ions. In this case, the electrode that you use is the metal electrode. The second case is a non-metal in contact with its aqueous ions. So in this case, you need to use a metal electrode that can conduct electricity, but the metal electrode should be inert, so we use a platinum electrode. And the last case, ions of the same element but in different oxidation states. So again, we have to use a metal electrode, but the inert one. So again, a platinum electrode. Okay, so let's take a look now at the example 1, where a metal is in contact with its ions in water. The example used here is zinc 2 plus and zinc metal. So like what has been mentioned, in order to measure the electrode potential of this zinc half cell, you need to connect it to the something called the reference electrode, which is SHE, which stands for standard hydrogen electrode. And to measure the standard electrode potential of the zinc half cell, it has to be carried out at 25 degrees Celsius or 298 Kelvin, and the aqueous ions concentration is 1 mole per dm cube, and you need to know how to draw these setups. Let's take a closer look at this zinc half cell when connected to the SHE. So compared to hydrogen gas, the zinc will be preferentially oxidized. Okay, so the zinc solid will be used up. So you will notice the mass of the zinc electrode getting smaller and smaller. So the electrons will flow through the external wires towards the SHE. And because zinc is oxidized, zinc is the anode and zinc is the negative electrode. Now remember from the previous slides, when the zinc half cell is connected to the SHE, the zinc is the one that is preferentially oxidized. So what will happen at the SHE is that the hydrogen ions in water will accept the electrons. It undergoes a reduction. Okay, so platinum is the cathode and platinum is the positive electrode. So remember I was saying in one of the previous slides is that to measure the standard electrode potential, you need to connect to a reference electrode which is called SHE, and if oxidation is favored, the electrode potential, or in this case the standard electrode potential, will be negative. So in this case we notice that the zinc is the one that is preferentially oxidized. So that's why it has a negative standard electrode potential for the zinc 2 plus slash zinc half cell. Okay. Now let's take a look at case number 2, where a non-metal is in contact with its aqueous ions. So essentially we have chlorine gas bubbling into water that contains the Cl minus ions. So because we are measuring the standard electrode potential, as you can see by the symbol with a capital E and that superscript, everything has to be kept at 298 Kelvin, 1 bar, as well as 1 mole per dm cube. Okay, so we will need to have one that is SHE and one where we have the chlorine gas bubbling into the chloride anions. Okay, so this is the whole setup and you will need to know how to draw it. Now when SHE is connected to the chlorine gas that is bubbling into chloride anions, in this particular case, the hydrogen gas is the one that is being oxidized. So you will not see bubbling at the surface of the electrode. And since hydrogen gas is being oxidized, this is the place where oxidation occurs, and this is called the anode, and SHE is the negative electrode. Now, from the previous slide, remember that SHE is the one undergoing oxidation. So there are now electrons flowing into the chlorine half cell. Okay, so the chlorine gas will take in the electrons to form chloride anions. So this is the place where this is the place where reduction occurs. This is where the platinum solid is the cathode and the platinum is the positive electrode. So now for the standard electrode potential of the chlorine half cell, okay, so remember the hydrogen gas is being oxidized while the chlorine gas is being reduced. So compared to the SHE, chlorine gas is being reduced. So reduction will mean that the electrode potential or the standard electrode potential of the chlorine gas is a positive value. This is in contrast to case number 1, where the zinc has a negative standard electrode potential. Now for the last case, which involves the same element but in different oxidation states in water. So the example here is Fe3 plus aqueous and Fe2 plus aqueous. So how can you draw to measure the standard electrode potential? You have to make sure the two aqueous ions are 1 mole per dm cube and at 298 Kelvin. So you need to know how to draw this setup. So when the Fe3 plus and Fe2 plus half cell is connected to the SHE, for the SHE side, the hydrogen gas is the one that is preferentially oxidized. So this is the place where there is an anode, and the platinum electrode in the SHE is the negative electrode. So now, when the Fe3 plus slash Fe2 plus half cell is connected to the SHE, the hydrogen gas is the one that is preferentially oxidized. So therefore, Fe3 plus will receive the electrons and be reduced to Fe2 plus. The experimental observation is that the color of solution changes from yellow to green. Okay, this proves that Fe3 plus is reduced to Fe2 plus, and this is the place where there is a cathode, and the platinum electrode is the positive electrode. So what will you observe around the platinum electrode at the cathode side? So this is the color change. So now what we'll do for checkpoint 1 is the test you on your ability to write down the electrolyte and the electrode for different cases. So we'll do it now. So for Al3 plus to form Al solid, the electrolyte is of course the aqueous ions. But if you want to measure the standard electrode potential, which is denoted by this superscript here that I've circled in red, so we must use 1 mole per dm cube. And the electrode for part A will be the metal itself, the aluminum solids. Now for part B, you have the 2 metal cations in different oxidation states. So the electrolyte will have 2 components, the Cr3 plus as well as the Cr2 plus in water, both of which are in 1 mole per dm cube. And the electrode, you have to use an inert metal electrode, which is platinum. For the last practice question in checkpoint 1, now for the electrolyte, you have to be very careful. There are a total of 3 ions, all of which have to be in 1 mole per dm cube. And the electrode here will be the same as the previous one. You need an inert metal electrode, which is platinum. So now to give a summary of today or lecture 1, the cell that we are studying today is called a galvanic cell. A galvanic cell is a spontaneous process. It involves the conversion of chemical energy into electrical energy. Anode is the place where oxidation occurs. Cathode is the place where reduction occurs. Okay, and the polarity of electrode is as such. The anode is negative, while the cathode is positive. Electrons flow from the anode to the cathode always. Okay, and you need to know the terms called electrode potential as well as standard electrode potential, which is given by that symbol that I'm going to circle in red. Okay, so what does the standard electrode potential value tells you? So if you have a very positive standard electrode potential, it tells you that the species prefers to be reduced. If you have a negative standard electrode potential value, it tells you that the species prefers to be oxidized. And there are 4 factors that will affect the electrode potential value. So one of them is the identity of the species you are talking about. The other one is concentration. Another one is temperature. And the last one is pressure. Okay. To measure the standard electrode potential of a half cell, we have to keep it at 298 Kelvin, 1 bar, as well as 1 mole per dm cube for aqueous ions. To measure the standard electrode potential of half cell, you need to know that it has to be connected to something called the SHE, which stands for the standard hydrogen electrode. The standard hydrogen electrode has an assigned value of 0 volts. Okay. And then you also need to know how to draw the SHE paired with 3 different types of half cell. And that is the end of lecture 1.